type solids that were created by rotation. And at the end, we started to talk a little bit about what if a solid was created by cross sections. And so what I thought I would do is give you kind of a view of this, similar to what we did with kind of the computer and the Play-Doh last time. I'm going to give you kind of a three-dimensionalized perspective view on this. So if you would, picture with me off to the side here. I'm going to draw in the y-axis like that, and the x-axis like this, and then my region would then, in perspective, maybe look like this. Does that make sense visually? So like the y-axis, we're trying to make it look like the y-axis is going somewhere off into the distance. Make sense? Where?
I said bueno.
Bueno, good. Okay, so then if the cross sections are perpendicular to the x-axis and they are squares, then maybe they would look like this. Or like this. By the time I get out here to the end, they'd be pretty small. Same thing on this end. So just attempting to kind of sketch out what this might look like. We could obviously fill in a lot more of them. It's kind of a sense. You really don't have to be perfect at visualizing this. You really don't. I mean, somebody could, I think, easily execute all this without a really good visual on it, but I think it helps a little bit. Okay, so as far as what you do, if you remember from last time, the formula that we looked at was for cross-section, volume equals, where did with the cross-sectional area formula, where did the pi come in? Was it kind of like rotation, pi integral, or was it somewhere else? Remember from those formulas? Let me ask you this. With those rotational formulas, why was the pi even there? You know what I'm talking about? Pi r squared. And why did the rotational formulas involve pi r squared?
Because it was a cylinder.
Yeah, it was like a cylinder, like a thick circle, right? So a cylinder involves pi r squared h. So for these cross-sectional formulas, where's the pi going to come into play? Come on. Feel free to look back if you want. It's not in it, is it? It's not in it at all. Nick, I saw you go. I wasn't sure what that meant exactly. I take you down that path because of this. Too often we get into a rhythm, kind of like, you get on your homework and you just sort of like motor through all these questions, and you think pi shows up in all of them. The pi will only show up in one of two cases. Either if you have some kind of rotation going on, which we've done that a lot, or what would be the way a pi could show up in one of these cross sections?
It's like a semicircle.
Yeah, if the cross section was a semicircle. You get it? So the cross section is a semicircle, there's going to be a pi here. But if the cross section doesn't involve some kind of a circular or elliptical shape, no pi's in these at all. Make sense? Okay, cool. So then volume equals the integral of a of something d something. So let's figure out our variable of integration. Is this going to be a of y dy or a of x dx? Which way is it going to go? It's going to be x's. This is going to be x's. Caitlin, why is it going to be x's?
Because it's perpendicular
to the x-axis. Perpendicular to the x-axis, yeah. So the same principle, though, like we did with rotation, that still applies. The thickness will be measured on the scale that whatever we're perpendicular to, it's going to be that. So we're perpendicular to the x, so it's going to be a dx. The next thing I would suggest we do here is think about our limits of integration. So if I've got these representative squares that are perpendicular to the x, am I going to be accumulating them from the left side to the right side or the bottom to the top? It's left to right. It's the same kind of principle we've done with the rotation. So left to right would be from 0 to what? 0 to 4. Yep. And this one, this is, you guys recognize this old shape? Didn't we do a ton of these questions with rotation? Do you guys remember the old region here? No? Isn't this y equals root x right here? And isn't this y, is it x over 2?
Yeah.
Okay. I just want to make sure we had the equations for that, but if I remember right, that's what it is. This is the same region, that region R that we looked at, I think 4 different times with rotation. Same region exactly. Okay, so it's integral from 0 to 4, and it is square cross sections. A stands for the area formula for a cross section, right? Because you can see that those squares on the ends are going to be really tiny, but in the middle they're going to be bigger. And so there's no one set cross-sectional area. It's got to be a formula. So what is the area formula for a square? I think I'd go side squared simply because that is much more compact than base times height. It would end up being the same thing in the end. I'm just going to say blank squared, and technically it's side squared dx. So our final task would then be to figure out, well, how long is the side? Can you guys tell me what is determining how long the side of the square is? The functions, agreed, because you can see that basically the square starts at the blue function and ends at the red function, right? So then how do we use the two functions? Say again?
Red minus blue.
Red minus blue. Yeah, wouldn't that give you that length? That would then give you the other side lengths of the square, because it's a square. They're all the same length anyways. So I would go red minus blue. That would give me root x minus x over 2. What if you messed this one up and you wrote x over 2 minus root x? What would happen?
Squared, so it would matter.
In this case, it wouldn't matter at all, would it? Because you're about to square the difference. That's exactly right. So if you flipped it around here, it wouldn't really matter. In other cases, with like big R, little r, it would very much matter. If you did like little r squared minus big R squared, that would very much matter. So be careful and try to do it right like you did. But in some cases, you might just find that you luck your way into it and it's all good. It might work out that way. So if you guys would either use Math 9, I don't know. You could do this without Math 9. I'll leave it up to you. Either use Math 9 or do it on paper. Let's figure out what the answer would be to this one, because it does say find the volume of the solid. Any questions while folks are running the numbers on that?
Why is it squared again?
So A of x stands for
The area.
the area formula for the cross section. So I'll just put area of a cross section. And so if the cross sections had been, say, rectangles, then you'd put a base times height right there.
Right.
If they were triangles, you'd go 1/2 BH, whatever.
Oh,
But
it
since
says
they were
square,
squared, it
so
would
that
be
makes sense.
side squared.
Right.
So just adaptable.
Right.
You can really make them whatever you want.
Right.
Yeah.
I don't know if that's the equation, but it's this one. Good.
Yeah. And you'll see some other examples here in a second of what it could be.
Right.
Okay, what'd you get?
533.
Okay. Are you guys getting that for a volume? 0.533. Seen that?
Yeah.
3-4 times here. How we doing?
I did it on paper.
Good? Good? Bianca, you doing good?
Oh, wait.
Peyton, going okay? Cool. All right. So let's move on. Let me please. Yeah, this will be good. I think number 6 would be an excellent comparison. Will you guys try number 6, please, on your own? We'll check your answers in a little bit. So read it over. Yeah, number 6.
You all.
0, 3.
Yes, ma'am.
Integral 0 to 3 of x squared minus
Like, I would just draw a square here, and it would be perpendicular to the y.
This just something we can use. So my circular base would look roughly like that-ish. So then if we're perpendicular to the y-axis, then these squares, maybe I'll draw in one or two of these, would look about like that. It's not great. Makes sense? Then you could have another one right here, maybe. Be a little taller. Maybe something like that. And then a little itty bitty one out here on the end, like so. Does that go okay with the thing you saw in the GeoGebra? Is that okay? Okay. So then as far as how we do this, I would recognize that we have cross sections. So we'd go volume equals integral of a of something, d something. This time did you guys use x's again, or did you use y's this time? Definitely y's, because we are perpendicular to the y-axis. Okay. So a of y dy. So then volume equals the integral from where to where. Where would you start accumulating and where would you stop? Yeah, so you start accumulating down here. Since the radius was 3, that's negative 3. You'd stop up there, positive 3. So negative 3 to 3. And then side squared is the area formula for a square, right? Now here is where it gets interesting. Let's see here. I'm going to use a different color, so please look really carefully. I'm going to use purple for this. So would it be fair to say that this that I'm highlighting in purple, can you see it? That is the side length of a square, right? And you can also see that depending on where you are on the base, that side length is going to be shorter or longer depending on where you are, right? If you're right in the middle of the circle, it's going to be longest. If you're at either end, it's going to be shortest. So it's going to vary. So we can't just say that the side length is like 3 or 6 or whatever. We can't really say that. But we got to express it somehow. Any ideas? Okay, solve for x. I think that's not bad because we need to have an expression with a y. So let's do that real quick. So it'd be x is equal to technically plus or minus square root of 9 minus y squared. Yeah? What do we do with that? Any ideas?
Then isn't each side equal to 2x?
Isn't each side of what
The squares?
equal to 2x?
Yeah.
Why would you say that?
Because it goes from one side of the circle to the other, and
So it goes from one side of the circle to the other, like that?
yeah, like
The
that.
2 green dots? Okay.
Yeah, and so
Why then 2x?
because the length on each side of the y-axis is equal, and that length is equal to x.
Are you hearing him? He's saying it really well. And isn't he right? So here's a trap. You might have been trapped into doing this, and I'll show you a couple different ways to think about this. You might have been trapped into just doing root 9 minus y squared. Do you see why somebody might have done that? And the truth is, if you did do that and realized, oops, you could actually really easily recover from this, and we'll talk about that here in a second. But he's right. He's right. The distance from, let's see here, I'll put it like this. The distance from the yellow dot despite the lack of perfect proportions in my picture, the distance from the yellow dot to either green dot is x, isn't it? From y-axis out to the left or y-axis out to the right. So if you wanted to, you could say that since this distance right here is x, and that distance right there is also x, couldn't you then say that the full length of the side of the square is just what Jack said? Two of them? 2x? Does that make sense? So then you'd replace the x with what x is equal to, which we just found earlier. So that was definitely a useful thing to do. So you would say 2 times the square root of 9 minus y squared, right? And that would give it to you. Okay? So then as far as solving this out and actually finding an approximation for the volume, I don't think this is... no, this would go okay. You could do this. Yeah, you could definitely do this on paper or via the calculator. What did you get here? Exactly 144?
Yep.
Okay. All right. So can anyone think of an alternative way that you could have set this one up if you had to do this on paper? Like, let's say the calculator wasn't active. What could you use? What could you do that would have made this a whole lot easier on the details to finish up? You'd still get the 144, but it would have been easier on all the in-between steps. What could you use? Yeah, no.
0 to 3 and then double it.
Why?
Because it's symmetrical.
He's right, isn't he? So, yeah, I think I would set it up exactly like you said. I would go volume equals integral from 0 to 3 of the exact same thing right here. Wouldn't that give you exactly half by symmetry? So then if you take Noah's advice then and double that, you then get exactly the same answer. So if you want to use symmetry, you're welcome to it. And if you were going to do this on paper with paper and pencil, I would suggest it, right? Because now you got a 0 in there, which is going to make your FTC one that much easier. So that's definitely a good find. I would do that if you had to do it on paper. Okay, you guys get the hang of this? Any questions, follow-ups of any kind? Okay, cool. So then, let's see here. I think I want to do 7. Yes. 7. Can I give you just a smidgen of help? What is that thing? It's an ellipse. Centered where? Centered at 0, 0. Agreed. And then there's going to be a 25 and a 9 involved for sure, right, as far as major and minor axis components and all that sort of stuff. So I'll just kind of let you explore with this. Feel free to use your calculator to kind of get a sense of what the graph might look like. Use that. This time the cross sections are rectangles. They are not squares, so we're doing something slightly different here. So explore and hopefully succeed. If not, it's cool. We'll work together. So I want you guys to try. Ready, set, go. Oh. Are you guys comfortable if I drew in the cross section like this, perpendicular to the X? Does that make sense? We're looking straight down on top of the cross section. No, I can see maybe it's not. So if we did our kind of standard perspective view, the ellipse is now going to look something like this. And so then the square cross sections, or rectangular, sorry, would look like that. Does that make more sense? See, on the right, we're kind of looking at it in perspective, and on the left, we're looking straight down on top of it. So if you think about it, if you look down on a sheet of paper, we know it's a rectangle, but if you look straight down on it, doesn't it just look like a line? That's why that red line is a red line, because we're just looking straight down on top of it. Okay, so then let's set it up like this. Volume equals the integral from, we'll figure out from where to where here in a second. But then its area of the cross section is just going to be base times height, right? Because it's a rectangular cross-section. So I'm going to say base, whatever it is, times height of 3. And then is it going to be a dx integral or a dy? Dx, because we're always going to be, we're perpendicular to the x, so it's going to be a dx. Okay, let's talk about limits of integration. If I've got a vertical representative element, like that red rectangle is, am I accumulating from left to right or bottom to top? It's left to right. Okay, so if it's from left to right, where would I start accumulating? And where would I stop? 3. So negative 3 to 3 are my limits. And now my final step would then be to figure out what the base length is. You could do this in a number of ways. I'm going to kind of use the same strategy I did before. If I look from purple dot to purple dot right here, isn't that half? I'll make a purple line segment in there. Isn't that half of the base? And if I wanted to describe that distance, what would I call it? I would call it a y. And don't we have the exact same thing down here between the purple dot and the other purple dot? So this is also y. So if you wanted to, you could say that this is 2y. But we would not leave it like that simply because it's got to be in terms of x. So what I'm going to do is put 2 times something in terms of y, or something in terms of x. I can get that by solving for y. So come over here and do that. If I was going to solve for y, let's see here, it would be 9y squared equals 225 minus 25x squared, dividing by 9. I guess that'd be what, 25 minus 25 ninths x squared, square rooted. So I think I could just import that in and say 2 times the square root of 25 minus 25 ninths x squared. Okay, so then you use, hopefully, Math 9 and be on your way. Did anybody use symmetry? You could have, right? You could have just gone 0 to 3 on your limits, doubled it. That would have worked too. If we're going to use Math 9, which I think we'd for sure do here, I don't think we'd need to do that, but you certainly could. Okay. What, did you guys get an answer?
141.372.
Say again?
141.372.
You guys agree with that? 372. Okay. Any follow-ups? No follow-ups at all? Okay. So, this is going to work out really beautifully. We're going to do just a little bit of geometry before we leave. So lead us into tomorrow. So tomorrow what we're going to do is we're going to do our final example, and we're going to kind of build towards it, and then we'll do some practicing, do the same thing on our next class, and then we'll have our quiz at the end of the week. Number 5. So I want to kind of help you guys lay some groundwork for number 5 for next time. What are the cross sections on number 5? Equilateral, specifically equilateral triangles, really important for us to realize that. What's unique about equilateral triangles? Please, at this point, hey guys, at this point, don't feel like you need to write a whole lot down. If you are going to write a lot down, relegate it to a pretty small corner of this. Okay? You don't have to write anything down right now if you don't want to. So equilateral triangles have all sides the same length. And what are the angles? All 3 of them. They're all 60. So that's really important because if I look at a generic equilateral triangle, say, looking about like this, I could label this, I don't know, maybe just with an X, this with an X, and that with an X. So when it came time to find the area of that equilateral triangle, you might find that this is a little harder than you originally thought, right? Because you can't just say 1/2 times base, no problem there, but then what's the big mistake? Times another X? Because looking at this, you can clearly see the base is X, but can't you clearly see that the height is definitely not X? Because this angle here and this angle here are both 60s, making neither of those X's vertical, meaning that neither of them is an actual height. Where would the height be? It would actually be, right down the middle. So the height could be illustrated by this. like so. How could I, yeah, now we're talking. So how would we find this? Come off to the side here and say, well, if this really was 60, then this is now a 30. And more importantly, perhaps, that's a 90. Right? Because if you drop an altitude straight down either an isosceles or an equilateral, it means it's perpendicular to the base. This is still the height. What is this side right here now?
1/2 x.
Yep, 1/2 x. This is still x right here. What could I use to find height?
Wouldn't it be 1/2 x root 3?
You could use, yeah, a nice proportion with one of those special triangles. What else could you use? Pythagorean theorem. Yeah, you could go either way. I don't know. What do you guys think? Would you rather do proportions with a 30, 60, 90 or Pythagorean theorem? Should be the same answer. What do you guys think is easier? Yeah, it was like a mix, right? So you need to pick what's going to be best for you. If you did do a proportion, you could do a 30, 60, 90. So it'd be 1, root 3, and 2. So then you could just use any two pairs of sides. You could say something like root 3 is to 1 as h is to x over 2, something like that. And then you'd say then that h is equal to root 3 x over 2. So if that's your height, you could then take this and just import it right there, giving you an area. It would be root 3 x squared over 4, where x is the side length. Anyways, I just wanted to throw this out there to you. I think it would be a pretty rare situation where you'd have to do all of that geometry, say on an AP test or something like that. But I wanted to point out how adaptable that area formula needs to be or could be within that cross-sectional volume integral. Something like this will come into play for sure next time. We'll kind of run with this when we get to class tomorrow. But for now, let's leave it alone. And when we rejoin tomorrow, we'll finish and practice. And that'll be that. No more new stuff. Hope you guys have a great day. Thanks.